people. And here is my current state on the Collatz conjecture, explanation, proof, whatever you want to call it. It's not really proof, but here's the thing. I know what I don't know, and thank you to Dr. Gupta, a mathematician I was able to get in contact with to help me analyze and be able to find out where I'm lacking. A couple of things on the first part, everyone always talks about it being positive and negative. Well, there's a domain asymmetry between the positive and negative, and you need to do things like, well, I wrote it out. So for the positive ones, you've got n is greater than 1 for n equals 2x, right? And n is greater than 1 for 3n plus 1, but 2x plus 1 is n is greater than or equal to 0 to get the first odd, x equals 0. Right, so you have a domain asymmetry as soon as you hit into negatives, which means you have to work it, right? So you have to, 2x is the same whether if x is going to be negative, right? We're going to negative integers. Anyway, this should be self-explanatory, but I guess I'm going to walk through it anyway. Right? Domain asymmetry, you multiply a negative 1 through here, you know that x is going to be negative. So 1 will be negative 2, x is negative, this is negative term, 1 goes through. If you're going to do that to the next process, you multiply that by negative 1 to get it through, right? So you're going to get a negative y. N is going to be negative because this is negative, so that's negative. And you don't have to negate the 3, only one of those has to be negative. Then it's minus 1 equals negative y, right? Negative integers, positive integers. There's a domain asymmetry. All you have to do is multiply this entire process by negative 1 and you alleviate the domain asymmetry. The domain asymmetry should move it by 1. Instead of starting at 0, it would be like negative 1, right? 2x plus 1 to make negative. Negative 1 has to be 2 times negative 1 plus 1. So you can't move this into negative without a domain asymmetry. I didn't realize that was a big deal. I didn't realize that was something that was... I didn't know that that wasn't really done a lot. Anyway, but these things bring out a little bit. This right here, I'll come back to this because this is how you can, the rules around substitution. But I want to go into this because right here we've got things like this, where if you take 2x plus 1 and substitute it in for 3n plus 1, that's 3 times 2x plus 1 plus 1. Same with here. If you have 2x minus 1 and you substitute it into the 3n minus 1, you get 3 times 2x minus 1 minus 1. These come at 6x plus 4, 6x minus 4. These fit into the positive coprime and the negative coprime theorem when it comes to 6. Right? 0 through 5. I shouldn't have to sit here and go through. If you don't know what a coprime is or what the coprime theorem is, there's tons of resources online. It basically is everything's in this one, everything's a multiple of 6 or 6 plus some remainder, right? Some mod. I'm learning modulo or modulus language too, so that's a new one for me. That's fun. Modulus math, I think it's called. It's got some name to it. Same with this one, right? There's every negative one is basically the same. It's a multiple of 6 or 6 plus some remainder less than 6, because then you want to be the next one would be x plus 1. Fun little part about this is you can break this into a lot of things. One is 2 times 3. These are all the evens, which are all multiples of 2. And then you have 3 times an even number and 3 times an odd number. 3 times an even number plus 1, 3 times an odd number plus 1 plus 2. All right, so you get this breakout of extra of splits in the coprime theorem. 3 times an even number, 3 times an odd number, right? Everyone following that so far? 3 times an even number plus 1, 3 times an even number plus 2, 3 times an odd number plus 1, 3 times an odd number plus 2. All right. So 6x plus 4 happens to be this one. This can't be a power of 2. These two can. This can't ever be a power of 2, just like this can't ever be prime, right? This can't ever be a power of 2. This can't ever be prime. These two can be prime. These two can be powers of 2. Again, should be obvious. If it's not, Google coprime theorem. At this point, this is where I want to make a point of 3 times an odd number plus 1. 3 times an odd number plus 1 is this, right? You can do the algebra and it gets there. More importantly is what it does when you go through this. So you get here, you divide this by 2, you're going to get this. Again, basic algebra, right? Well, here's the fun part about this. Take the 2, this could also be some power of 2, right? 2 times 2 to the z, or alpha, or something. I don't even know if I have another one. I think I do alpha a, 2 to the a, some power of 2. Take away that power of 2. Now, at some point in time here, you're looking, anything that this x is, whatever this starting value in the x, right? When you're looking at it as an entire split out over into the positive integers, or in this case, the negative integers on the other side, this is every integer, 0 through to infinity, right? So right up somewhere in here, you're like, you can't tell anything about the parity here, but once you start doing this, you can. And I did red and blue to illustrate red going towards 0 and blue going towards infinity. And I did the same thing on the negatives here, red going towards 0 and blue going towards infinity. Simply to illustrate the difference. And so you can see right here in this 6x plus 4, once you start dividing by any power of 2, you get this 3x plus 2. Well, here's the thing. 3 times an even number plus 2 is over here, right? This can possibly be a power of 2. So like this can be a power of 2. This has to be even to be a power of 2. This has to be odd to be a power of 2. Let's just get through that. If this is an odd number, well, it plops out right over here. And if you were to look at this and be like, well, what happens about this 3? Well, here's the thing. Right here, if this one, which is also an even, happens to possibly be a power of 2, if x is an odd number, well, this can be a power of 2. And this would just be 1 power of 2 less, and vice versa here, right? So this is 1 higher power of 2 versus this if x is even. So this is how you can get the evens. And if you look at it in a certain way, it's like, well, 0, 2, right? If x is 0, which is an even number, 3 times 0 is 2. Get what I'm saying? 3 times an odd number, which would be the first one, would be 1, right? So x equals 0, x equals 1, x equals 2, x equals 3. Let me bounce. So odd values of x will have a power of 2 there. Even values of x will have a power of 2 there. So even can drop you into a power of 2, and odd, once you get the 2's out, once you get it out of the composite, will always pop out over here. Now the next one after that can be different, and in fact, in order to illustrate this, because once you start going to the next one, you need to, the past value of x isn't necessarily what you need to go by. What you need to do is substitution. Here's the little algorithm. Once you're at this 3, you divide it by 2, now you've got this 3x plus 2. If you can't continue to divide, that means this x is odd, right? If x is even, you can keep going through 2's all the way till you get to one that isn't, right? Some power of 2. Till you get to a version of this that's odd. Actually, I shouldn't even say that. It's 2 to some power, right? You can keep going. As soon as you can't anymore, this is going to be odd, which means x is going to be odd. You just replace it with the odd, right? Whatever this is, so this term becomes this. Well, whatever this x is what's going to determine. It's not that the number changes, right? These 2 are the equivalent number for any odd value of x. 3 times 3 plus 2 is 11. Okay, that makes k 5, right? So, but more, I'll get to another part. You can replace this. And by these rules, if k is odd, you just immediately, right, you can't divide any more 2, so you immediately plop it right back into this. You'll get your next number by this, right? You're like, okay, so this is an odd number. We do multiply it by 3, add 1. That's the Collatz thing, right? If an odd number, you multiply by 3 and add 1. So this is an odd number. Replace it with that form. Doesn't matter if it's 11. It just means that the next value that's going to put in here, if this one's 3, the next one's going to be 5. If this is 5, is the next one. It's where the next bit is. Because honestly, if x is 5, right, this value is going to be 17. 17 minus 1 is 16. All of a sudden, you can divide this by 2 forever. But you don't. I want to say there's an intuition of mine that wants to say if it's going to be of this value where this is a power of there, I want to say that you could divide it by 2 twice, but I don't know that for sure. And there's probably a value where that isn't true. I want to say it can, but without that, I'll just say you just do the one division. So like if this is 16, you go to 8 and then replace 8 in here. And then do the division after, because then you would get like 3 times 8 is 24 plus 2 is 26. You divide that by 2. It's not the only one. It's not necessarily the best example. But then you divide by 2 again, right? If k equals an even number, or if the entire thing is an even, you still have to get the 2's out. But you can't do it when in k, you have to do it over here, right? Because once k is a power of 2, you divide to 0, and you can't do 3 times 0 equals 2. It breaks it. So you can't do that. Essentially, what you're saying is this is real. Like the k value that you're talking about was a power of 2. So, and then when it's even, it'll go, you divide by 2. Like if this happens to be some other number, like what would it be? I don't even know if that's possible. Now that I'm thinking about it, what would be a value of that? That would actually be 3. I'm not even sure if there can be an even number that'll pop up in there of k, but maybe. But even if it is, you would just do that much like we just showed with thing where you do 3 times 8 plus 2 is 26 divided by 2 is 13. And then your next value would be 13 minus 1 times is 6. Okay, so there it is right there. Yeah, there is definitely a possibility for it. Right? 13 is 2 times 6 plus 1. So then k equals 6. 3 times 6 plus 2 divided by 2. You just keep going down to 3. So then you can get 3 times 3 plus 2 is, and you go down. Anyway, it should work for all values. Basically because you're plopping the same values right in here. And you're like, okay, so if I get to an odd, it's going to be there. Once I divide all the powers of 2 out, it'll be back here, and I can drop it in. You're like, what about all these other ones? You were just talking about 13. Yes, the overall value, right? The overall value can be any of these. The x value will follow this pattern. And it's completely contingent and dependent. There's a couple, I want to say, and this is where I don't have the language to go farther than this. This is where I know what I don't know. I don't know how to properly explain this in formal language from this point on. I'm going to keep working on it, but I don't know how. What I can say is it goes up, down, right? This is if you have evens, and this is if you have odds. Odds go towards infinity, evens go towards 0. This, the pure algebra of it, I think makes us, I want to say sync a tractor around, there's 2 ways. Like if you were to do 3 times an odd number plus 1 to get to this power of 2, or 3 times an odd number minus 1, right? 3 times an odd number minus 1 to get to this power of 2. You create 2 different, this is a process, an iterative process, right? So you create, I want to say attractors or sinks, or I'm not really sure if the proper term of it, but this one, even though you go here, it creates a vortex, attractor, sink around this. This one creates it around here. Without doing the arithmetic, there should be a domain asymmetry if you try and use this over into the negatives on 5. On 6x, like say negative 5, right? 6x minus 5 when x equals 0, which it can't, because if you're doing there, right, it wouldn't equal 0. It has to equal 1, but you can't. There's all that blah, 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 blah. If you try and apply this positive to the negatives, you should get, instead of being here, it would be here. Instead of starting at 0, you got to shift it over 1, so you should have something here. Which would also mean a weird thing here is, anyway, yeah. If we were to go the opposite way. And the same thing happens if you do the negatives. If you do it properly, if instead you do a split definition at 0, so all negatives have to do that 2x minus 1 and 3 and minus 1, right? So now you've got the same thing where you've got the negatives. I did the same thing. The reds go here, or basically evens go towards 0, odds go towards infinity. I don't know how else to say this. The runaway odd in this particular case would basically say that no matter which iteration through here you do, it would never have more than a single power of 2 here in any factor. I don't think that can happen. Since it's creating this algorithm, it's basically popping out here. Okay, we'll drop it back here and add 1, and we'll divide all the 2's until you get to one of these again. You can get all these numbers because once you start dividing by 2, these numbers can be anything, right? This value of x can really change what these are. But once you do the 3 times an odd number and add 1, you put it right into this funnel, algorithm, Turing machine. I don't have a proper name for it. I don't want to call it a funnel, but it just kind of keeps chunking them out. You get some number, boom, go for it. Is it 3 times an even number plus 1? I don't know. You shouldn't. You should always get an odd number, right? Or you can keep dividing by 2. So you should always get an odd number. Once you've divided by 2, it doesn't matter what this x is. If it's an even x, you're going to come here. 3 times an even number plus 2 is another even. You can divide by 2 again. 3 times an odd number plus 2 is these. Can you come up with a 13? Absolutely. Absolutely. As you do the iterations, these numbers can change. And they can be any one of these. You divide by 2, it's like, well, it doesn't matter. If it pops it out of here, you're going to have the same thing. What happens if you divide this by 2? Oh, you get 3 times something. Well, if that's an odd number, guess what? That's 3 times an odd number. Once you divide by 2, like multiply by 2, it'll come over here. Once you start taking these out, these can be just about anything. And that's why you get factors. But once you start rolling through, you keep getting factors that'll be the same. That's why multiple numbers will drop on the same factors. You're pulling all the 2's out and multiplying by 3, adding 1, dividing by 2. You're pulling it into those columns. It's a pretty robust algorithm. I want to say that the iteration process creates I'm going to use what might be improper terminology, but just so that I can at least have the same terminology, even if it's improper, I'll at least try and be consistent. There's like an attractor here. If you're going negative, it'll go through, how do I even put this? 15 and 17, I want to say. 15 you can divide by 3, right? And then you got an odd, or divide by 17, all of these things. If you do it, I want to say if you go to this negative route, but I'm just going to confuse things. You can't get to this, you can't basically multiply it by 3 and come to this one without causing loops. This one will always go around here. And like I said, if you change the domain so that you don't have 0 and you have to move everything over 1, it would plop it over here. And then you have this times a multiple of 2. But as long as it's right here, you have whatever you drop on. Number 1 has the possibility of power of 2 all by itself. 3 times an odd number plus 1 has a distinct probability of being a freaking power of 2 all on its own. If it's not, it'll still be an even number. And if the x that does that is even, it has a distinct possibility of being a power 2. If it's odd, if that x is odd, once you've gotten the power of 2 defactored, it should pop out here. Does it always? No. Because the odd number can be something else. You're like, you can get 30. Yes, because you start with a strange value, right? You start with a value that may not be this. If I come out here and say, I want to start with 2. Well, you can't do 2 because that's I just totally picked the bad one. I want to start with the number 3. It's odd. 3 times an odd number plus 1. 6 plus 4 is 10. right? I feel like I'm doing basic stuff, but I want to make sure that it's clear. There's things like the loop. There can't be a loop. There can't be a never-ending loop here. This will always kick it over. When you get an odd, it's never going to go back up. It would need to have an equivalency that it can't have. Here, if you were to go this way, it can. It would have an equivalency at 6x. The equivalency is here. I don't know the mathematics or terminology to say that it'll always circle around this value, while this one, while you're trying to get it to here, can circle here. I don't have that language. This is my next step in this evolution, is finding that language and people who can help me express this, because the loop can't happen, right? The eternal loop isn't going to happen. It can here, right? Where you have like, if this is 16, you have a problem with 17 and 15. Right? Anyway, 7 and 5. 7 and 5 will cause you problems. And 5, if you try and go negative, will, because it essentially goes right here. And I don't know how to express that as a better mathematical term. I don't. I'm going to learn that. That's something I have to learn. I can tell you, much like in Spanish, entiendo más de lo que hablo, pero no hablo mucho. I understand more than I can speak, but I can't speak much. So, goes up, comes down, goes up, comes down. Goes up, comes down, goes up, bam. This one requires an even number to kick it out. This one requires an odd number to kick it out. And these are the only two powers of 2. Right? This represents all positive integers across the inner number line. This represents all negative integers. There isn't an integer you're going to come up with that isn't one of these, right? Unless it's a fractional, right? Actually, that wouldn't be an integer. It'd be a rational freaking number, wouldn't it? So yeah. I'm not sure. Everyone's like, well, how do you know the number doesn't run away? It's a question where everyone wants to find a way to try and map all factors of all numbers and how they go through, basically, how each multiple of what number goes up. That's probably possible, but you don't need it. What I mean is there is a number out there that once you do it, it will collapse to another number. Because what you're saying is that there can't be just one number that does that. What you're saying is there has to be one number that once you do this to it, it has to collapse to another number that only has those. You're asking for an entire set of numbers that once you take out the factors will never, ever, ever have a higher than single power of 2 within there. And I believe even there's a fairly robust bit, if I don't misunderstand Terence Tao's proof out there, that's just for all but a trivial amount isn't going to happen. And I will tell you that according to this, the trivial case is the 0 case. Or 1 case right here, where this is 0, so this is 1, right? Where this is 0, because prime. Every other, just like the coprime theorem holds for every case but the 0 case. These are the only places where primes can happen, except for the 0 case, right? Because 3 is prime. When x is 0, 3 is prime. So it's 2, right? It and 1. 1's technically not prime, which I can't even begin to get the right verbiage for that. There are people who can explain that far better than me. But you're asking for a whole sets of numbers that will always do that. That whatever number you pick, it would need to loop back either to itself if there's a single number that does so, or there's an entire set of numbers that when you go through this, it will never happen. That there is a number such that when you say it's this, and it does this and hits here, there's another number here that will repeat through here that doesn't allow powers of 2 ever in that iteration. That's an entire set of numbers. And you're saying, well, no, because it's not even the primes. You're going to ensure if this is an odd, you're going to ensure that. You're talking about an entire set of numbers that do that, not just a single case. That's why I think the runaway odd is impossible. The loop, I don't have the proper math to say that it's here. Like if you were to go negative, it would be an attractor here, and going positive creates an attractor here. But that's my intuition to it. But I don't have the proper language to show it in a formal proof. But that's what's coming next. So there's my Collatz work. There's my progress on it. I'm going to get in contact with people and see what we can do. And that being said, everybody, happy Friday. This has been your dose of Drew. I'm said Drew. Let's see if I can't change the world.